And we will start with, where is my, where is, why, hold on, okay, let me find, oh, here. Okay, so today we will start with new material, a new kind of data structure called a graph, okay. And previously we learned a tree data structure. So there's some connection between tree and a graph. Basically tree, we can also say it's one kind of graph. Okay, so we will learn graph abstract data type, ADT. Okay, that's what we learn today. Okay, and then let's first get some concepts. Okay, so and based on tree, binary tree, we learned that so it's you have a node and then you have some. So we have node, is it? And then we have some we call arc, is it? And lead to another node, is it? Lead to another node. And over here we call some leaf node. Then we also have root node of those. And anyway, so it has node and arc, is it connected together, is it? But you can see for tree it's open, is it? It's you have some leaf node, then it's open, is it? And so what is the graph? And generally in either math also has graph theory, okay. And in CS, okay, we have graph and generally we represent as a G. And it consists of, it's a set of vertices. Vertices basically is node, okay, it's node, or we call it node. And normally we represent as V, okay. And it's a collection of edges, or we call it links. So we use a capital E, okay. And what is an edge? An edge is you connect two vertices together, then that's an edge. Okay, so like in this is a tree, is it? And if we add more, we connect more. So in this case, so this is node. And in graph case, then we call it vertex. Okay, and all of them together, we call them vertices. And you can also call it node, but generally when we refer graph, we call them a vertex. Okay, and what do we call this? You have a line connected to vertices, is it? Then this is called an edge. And some people also call it a link. Is it? So this is a graph G that has a number of vertices and a number of edges. Then we can represent as something like this, vertices and edges. Okay, so vertex we already learned, is it? So it's some node within a graph, okay. And the edge, what is the edge? Edge must connect two vertices, okay. And the graph, so, and we all know like airline, is it flight map? Is it sometimes if you go to some airline to show their domestic or international flight map, is it basically you can view also that as a graph in the real world, is it application? And then in that case, the vertex can be what? Can be like the airport, is it airport? And generally some within a city, is it? And what is the edge? And the edge then in this case, some flight, is it? Connected to airport, is it? Okay, so this is one example, is it like airline flight, okay? And in CS, like a computer network, definitely it's some graph, is it? And the routing, is it? Routing. And okay, and then next, let's see over here. Okay, and over here that's a tree. We already learned tree, but we mostly learned the binary tree, is it? And anyway, so tree is basically considered as a special kind of graph. Okay, and why we say it's special? Because it's only allow a single path from one node to the other. Okay, a single path. So let's take a look at that original one. Is it? We have that draw. So this is the tree. Is it? From it says single path from one node to the other. So it doesn't matter. Okay, if you consider from this node to every other node, there is only a single path. Is a single path. Then let's take a look in the case of graph. Is it? In the case of graph, from this node, you can go to the other node, either like along this path, or you can go to a detour. Is it? There are multiple paths. Is it? So graph can allow multiple paths. Okay, from one node to the other, or and as well as it also allow a cyclic path. Cyclic, it's you start from somewhere and you end at somewhere. Is it? So this is a cyclic path. And in tree, that cannot happen. Is it? There is no way you start at root and you come back at root. There is no way. Is it? So cyclic path is start at a source node and then you end at the same node. Okay. So that's a different. And later on in this graph module, we will also see a lot of time from graph, you can also derive a tree. We call it some like minimum spanning tree. So that's used a lot. Is it to find some tree structure from the graph? Okay. Okay, so that's the concept, a graph. And then over here, let's take a look. Example. So here, basically, I took this graph from a computer network textbook, okay, when I taught the computer network. And so this basically shows it can be a computer network. So computer network can also be handled as a graph. Okay, as a graph. So over here, generally when we draw graph, the vertex, we can use a circle as it, and you connect two vertex, we call it edge. So a link, is it? In network, we call it a link, okay? And in graph, we normally call it an edge. So then when we describe this graph, is it? And of course, for each vertex, you need to have something identify it. Is it vertex ID or label or name something? Is it? And the edge, then normally you use two vertex to identify an edge. So in this case, the vertex set, is it? It's unique. Every vertex is unique. So it is a set data structure, is it? So we can use a set data structure to represent all vertices in a graph. So then in this case, we use all its labels to represent A, B, C, D, E, F, is it? Okay, then for an edge, we can use a collection to represent it, is it? And it involves two vertex, is it? Involves two. So we can list out all of the edges. And what this diagram shows, it shows an indirect. So graph, we also have some category. And this category, there is no direction in this graph. Is it? So that means like for this edge, there is no direction shown. Is it? So that means it's a two-way. Two-way. Is it two-way? That means you can go from A to B and also B to A. Is it like a two-way road, not a one-way road? Is it? Or like a two-way flight or two-way network. Is it? Generally speaking, computer network is two-way. Is it? You can upload, you can also download. Is it? And you send to, you can also receive message. Is it? Okay, so this graph is an undirected, not just undirected, it's also unweighted. That's unweighted and weight we will learn. Is it because what? Because the edge doesn't have direction. And also edge doesn't have weight associated with each edge. So you don't care about the edge, you just care about if the two nodes are connected, okay? And normally, like if you describe like a friendship, because a lot of times the friendship can also be described using graph. Is it? Then in that case, you just care if you and the other person are friends. Okay, so there is not something you can associate to measure. Is it? Unless you say, okay, the best friend or close friend or just a general friend. Is it? But generally, when we describe friend, okay, just if you two are friends. Is it? But think about like a flight, airline flight. Then you have distance issue. As you may also have air ticket, as a plane ticket. Cost, is it? A lot of other stuff, or like the time it took to travel from. Is it? All of those. And when you want to consider those between two nodes, then that's called a weight. Is it? And here we don't have weight. So we call this graph is an undirected and unweighted graph, okay? Because later on we will also learn weighted graph. Okay, and then let's see this diagram. So in this diagram, it's not just show the edge, etc. And we also have this arrow on the diagram. We also have all of the arrow on the diagram. So it's kind of clearly see it's one way, not both way. Is it not two way? So this is still edge. Is it edge A but to B? Is it? It won't allow B to A. Is it? So edge has direction. Is it? Then in this case, so if all edge, be careful, okay? All edge have directions. Then this graph is called a directed graph. So here just some term, okay, directed graph. But still the edge doesn't have weight associated with it. So it's directed but unweighted graph, okay? Okay, then let's take a look. This one, this looks more complicated, is it? And each edge has direction, is it? Has direction, and not just that. And each edge also has some number associated with it, is it? So over here we saw that on the each edge we have some number labeled on it. Is it? So those numbers, we call them weights or costs. Okay, costs. So then this, you have some associated numeric number. Is it? Then this weight is called a weighted graph. Okay, this is a weighted graph. And what can be the weights? Like we previously said, is it like for flight, is it? Then it can be like distance or time or cost or maybe something else, is it? And for computer network, it's maybe link bandwidth, is it? And something else, it's also possible. So you can pick how you measure, is it? So then you have weight associated with it. And then just think about, you use map, is it? And we have GPS, is it? And so how GPS works for them to give you from a source and a destination. So you enter two locations, and it will give you the route. It give you the route, and within the route you can pick, is it the shortest distance or the fastest route. These two not correlate, is it? So then this can be placed as what? As the weight. As a weight or cost, is it? So GPS, they need some graph algorithm, okay? Okay, so this is weighted graph. And then next, let's see. Some other definition, it's relationship between two vertices. Okay, one is called adjacent. So what is adjacent? Adjacent is that if there is an edge connected, then we just call these two vertices adjacent to each other. Okay, then we can go back to take a look. So then in this case, A and B are adjacent. Is it? B and F is not adjacent. So adjacent, it's very clear. Is it A and B? Is it? And B and F, it's not adjacent. So if there is an edge connected, is it? A and C also connected, is it, in this graph? Okay, so that's the definition for adjacent. Then what is that? Predecessor and successor. So both of this concept need to be for directed graph. Okay, directed graph. So in a directed graph, for an edge, you have the starting vertex, you have the ending vertex. Is it? So starting vertex then is called predecessor of ending vertex. Okay, and then the successor, same thing. So ending vertex is called the successor of the starting vertex. Is it? So then let's get back the previous diagram. Is it? So then in this case, we can say A is B's predecessor when you consider this edge. But of course, if you consider the other edge, then B is also A's predecessor. But if we consider A to B, then B is successor of A. Is it of A? And because over here it shows both two-way, is it, both direction? But in this case, then it's clear, is it? So B's predecessor is what? Is A. Is it? But if you take a look some other one, like C, C's predecessor, it's not unique, is it? It has B, it also has D, is it? So multiple nodes can be the other node's predecessor. And the same thing for node C. For node C, node C's are not decessor. Let's take a look at the successor, okay? Successor, yeah. So let's see. The node E has predecessor of C. It also has a predecessor of what? Of D, is it? But let's see A. A has two successors. Is it? So successor and predecessor not one, is it? So in this case, it has B and D. Both are successors, okay. Okay, so this is just some term, because later on we will use all of those terms. Okay, then the other concept is how do we visiting vertices in a graph? Okay, so here's some concept is we can have a path, find a path. So path is what? Between two vertex, is it? So it's a succession of edges you visited. But be careful, okay, without repeated edge. So no repeated edge. Okay, so then that's called a path. Okay, a path. So let's go back to C. Suppose we use this example. Okay, we consider directed graph first. Okay. So then like path A to F. Is it A to F? You can find succession of edges. Is it? So A to B. Is it? And then B to C. And then C to F. Is it? So then you have this is a path, A to B to C to F. So we find a path, but of course not unique in this graph. Is it? You can also do A to D to F. You can also go A to D to C to F. You can also go A to D to E to F. There are multiple ways, is it? You can reach from A to F. But anyway, this is called a path. Okay. And then exit C. And what is called a cyclic path? A cyclic path is that a succession of edges visited with no vertex visited twice, and also without any repeated edge. So path doesn't anyway include any repeated edge. And a cyclic, another condition is there is no vertex visited twice. Okay, so every vertex just visit once. Okay, that's called a cyclic path. There is an opposite concept called cyclic path. Cyclic path is what? It's also succession of edges, but there is one vertex that visited twice, but no repeated edge. Okay, no repeating. So there is one vertex that's visited twice. Okay, visited twice. So let's see. In our, we use the directed one, okay, to think about it. So A to F, is it? A to F. So this is acyclic path. Is it? Because there is no vertex visited twice. Okay, no vertex visited twice. And let's see if in this diagram I can find, this is not a very good diagram for the other definition, okay. For the, so how about let's change this direction, okay. Change the edge between D and E like this. Okay, change it, reverse the direction. Then in from D to C to E and then to D. Is it? And the node D visited twice. Visited twice. Is it? But no edge visited twice. So then this is also considered a path. but this path is cyclic path, okay, because you have a node that's being visited twice, okay. Okay, so this is a concept regarding visiting vertex, okay. And then let's also see some special graph, okay. And we have some graph, we call it a cyclic graph. A cyclic graph, so what? A cyclic graph is a graph. I think I got it. A cyclic graph is a graph without a cyclic path. A cyclic path is, so then this graph, that doesn't, I need to double check with this definition, okay, if that's correct one. So let's go back to, let's go to the next one, complete graph. Complete graph must be undirected graph, okay, and undirected graph that every edge, so has an edge between every pair of vertices. Okay, so we can kind of, let's see, draw this kind of, so suppose this is graph, okay, and complete, it's undirected, and for this one, this is not complete because it's not every pair of vertex, you have an edge. So how do you make it? Then you need to have every pair, is it? So every vertex versus all of the other vertices in this graph, then it has an edge. Then we call it complete. Okay, we call, so then in this case, then we have it's with all of the, every single one, you needed to make this condition be true. Then it's called complete graph, okay. And then next, let's see, connected graph. So connected is also undirected graph, okay. And it says there is a path from every vertex to every other vertex. So then this is called a connected graph. So the idea is, but it's undirected, but you must have a path from every vertex to every other vertex, okay? So then in this case, suppose we just do a binary tree. Then is a binary tree a connected graph? And if you see there is a path, okay, from every vertex to every other, even though it has some open, is it? But if we do something like this, suppose we connect it, then we connect, and if you have, then if you consider all of this together, then definitely this is not a connected graph. Is it? Because between these two, there is no connection. Is it? There is no connection. Is it? So there is no path. Okay. So then it's not a connected graph. A tree is a connected and undirected, and it's also a cyclic graph, okay, a cyclic graph. So that's a tree. And the subgraph, there is another concept. Subgraph is you have subset of a graph's edges and associated vertex. Then it's, so you take a part of the graph's edges out, okay, then we call it a subgraph. Okay, so that's some just a special graph concept. And what next one try to discuss is about the applications with graph. There are a lot of applications, okay? So that's why graph is kind of important. So first is computer network. Okay, computer network. So what can be a vertex? Is it? So in computer network, you have like we call it an AND system. Is it an AND system? So like a PC or a mobile device, all of this, is it? And maybe also server. Is it, all of those can be considered, is it? And then if you want to, right now the global internet, is that you can global the digital information can travel, is it? So you need to have some kind of, we call it router or switch. Is it connected to the other device? Is it? Then, so the computer or switch, all of this, they can be vertex. Can be vertex. And the link, so the link, it can be wireless link, is it like Wi-Fi or mobile, is it like a 5G, is it? Something like that. And it can also be wired. Wired, is it like optic? Okay, and then all of those that can be considered an edge. So normally we call it a communication link. Okay, so that's one application in computer network. We use that a lot, is it? Because a lot of time for the routing, how you get connected, like your mobile phone with the other mobile phone across, maybe in Europe or in Asia, is it? How it's find the path. There are so many routers, is it? Find the path. So the routing, it uses the graph concept. Okay, like later on we will learn like a Digester's algorithm or Bellman fault. Okay, so various kind of routing algorithms. Okay, and airline industry, is it like the flight map? So definitely, and we all know like GPS, is it the Google map, is it something like that? And not just those physical, social network, they also use graph. So in social network, a person can be vertex, and then the relationship between two persons is an edge. Okay, and not just this, organizing the websites, the relationship between websites, we can also describe as a graph. Okay, because then this kind of website can be a vertex, and then you may link to some other website, is it? Then that's an edge. It's not just this, even in management, like later on we will also see. Okay, so project management can also use graph to describe the relationship. Okay, because one task may depend on the other task. So here task can be vertex, and the dependency of the one task versus the other can be a edge. So later on we will also see our like a topological like a numbering. That can be used for like a task scheduling, etc. Okay, so then in that case, you may count on graph theory. Okay. Okay, and then next, let's see. So graph, then the graph data structure, so previously we learned that like for stack implementation, that how do we describe the stack? You can use array, that you can also use linked approach, that like linked list, that to implement stack. And the queue, same thing, that we can use array, that you can also use linked approach, So depends, is it? We all already learned stack queue, and we also learned what tree. And when we learn tree, we learned the linked approach. And if you recall regarding that heap sort, that the heap tree structure, then we use array. As they use array, so tree not just limited by linked approach. You can also use array to implement a tree structure, etc. And then so depends on how you pick the different approach. Is it when you pick a linked approach, then you have node or like a bin node. Is it? So that's what you use. And if you just use array, so then it's just some single type item. Is it? So it depends. And then for graph, we can already see that it's more complicated compared with all of the data structure that we learned. Is it? So let's see. For graph ADT, is it? So graph, you can represent it is that using adjacent matrix. Okay, so later on we will see. So it's kind of you use a matrix anyway, it's a 2D, is it? So you have A, B, C, D kind of E. Okay, and then you have A, B, C, D, E. So all of this are vertex. You arrange it as some matrix, is it? So if A and B connected, then you put as a 1. If they are not connected, you can put as 0. So something like this, is it? So then it's a matrix format. Is it? Matrix format, then it depends. It can be a sparse matrix or a dense matrix. There's a lot of 0, a lot of 1, etc. So it depends, okay? So here is that later on we will come back to take a look, okay? So it says it's not going to be efficient due to the sparsity of the matrix, okay? And so instead of using matrix, so the 2D array basically, then that we can use list to represent the relationship among vertices. And if you do that, then it's called a vertex adjacency list. Okay, adjacency list. Then what it means is you have the vertices of your graph. Is it? So this is a V set. Is it? And here you have the adjacency list. So you have a list. Is it? So associate with this specific vertex, but all of its neighbor vertex, you're going to store them in a list. Then in this case, we call it a vertex adjacency list. Then if you have all of this be stored, basically you know the graph. Is it? If you know of the vertex, you know of the adjacency, you know the whole graph. Is it? Because what? Because the edge then can be derived, is it, in this case? In this case, you have the adjacency vertex, then all of the edges can be derived, as you have AB, you have AD, is it, regarding from A. Then from B, you have BC, BD. Is it? You can derive all of the edges. So once you know this whole set of information, you know the graph, is it? Okay, so that's one way we use vertex agency list. We can also not just use this, we can also have, we call it edge lists. Okay. Edge. So you have all of the vertices and you also have the edge associated with it. Then it's like for A, then you have AB, then you have AD. And then for B, then you have AC, you also have AD. And for C, then you have CE, and you also have CF. Is it? So you can also have an edge list. So that's another approach. Okay, we can design a graph. Okay, so all of this are just some concepts. Just some concepts, and the next one, let's go to our first very simple one. Okay, so this is that's what I designed. It's not the the best design. Okay, but I tried with a different kind of concept from the textbook ones. So in our, oh, I may not have posted, I will post it. So this is called Java Simple Graph. So we will start with this one. So we have 4 files, okay? We have a vertex Java. So vertex, we define a class. Edge, we define a class. And then we just call it a simple graph, a very simple graph. Data structure, okay, and then we have the application. So let's take a look, starting with vertex, okay. And for this vertex, it's a pretty simple class. And we don't need to worry of this. That's going to be used for later on stuff. Over here, we just care about, for each vertex, we have an ID, and we also have a string label, okay, to name the vertex, so that's easy for us to view, okay. So that's pretty straightforward. And we also have the constructor, okay, initiate its ID and label. And the toString just output this specific vertex, okay, as ID and the colon label. And when we define over here, that for the hash code, if you take a look, we just use ID, so we don't worry about the label part. And because if you recall previously, we learned hashing, etc. And in Java, it's recommended you make a contract between the hash code definition and the equal method definition. If you override, then you override both. And here, because your hash code use ID, so that's why the equals you define also use ID. Okay, use ID. And of course, you need to do some other check if it's instance, if the object itself. For the equals, if you recall, we have the 3 rules, okay, to define, override the equals. So we try to follow that to design recommendation, okay. That enumeration we can temporarily forget. Later on, we will come back. And then over here, we also design the edge, okay. And in my version, I design the edge as directed, okay. And U as starting index, and the V is the ending index. Ending index. So U to V, okay. So it's always like this, okay. If you have 2-way, then it's V as the ending and U as U as the ending, V as the starting, okay. So anyway, so we have edge and initiated, and we have the toString and equals, it's the same. We define equals, and we also have hash code. And this time for the hash code, we consider both vertex, etc. And that's why for the equals, the contract, you use both, okay. And here, you can use both and U and V because anyway, their hash code also defined, etc. So you can directly apply the hash call with the vertex. Okay, so this is our edge definition. Okay, then let's come back to our simple graph definition. And over here, I define it as a very simple directed graph. And directed graph, a lot of time you will also saw this word, see this word, digraph. Okay, so it's directed graph. Okay, and what I use it, the ADT, the storage for all of the information, I use a map concept here. Okay, just try to familiar us with the map usage. Okay, so for all of the vertices, I define it as a map. So what is map's key? Key is the vertex. Because anyway, in a graph, the vertex V is a set. And because it's set, it's each one is unique. Is it? And each one is unique, so it serves well as a map's key. Is it? Yeah, so that's why over here I pick vertex as key. And for all of the edge, so you have a vertex, is it? Then it can have multiple edge connected. Is it connected? So you will also, so in this case, it's two-way considered, okay? So it doesn't matter. So anyway, it's all of the edges, at least one vertex, no matter it's starting or ending, then you will store them in this list. So that's the value part. So key is a vertex. Value is what? Is or either outgoing or incoming edges. Okay, so list of outgoing edges and incoming edges. Okay, so that's my way to define it here. Okay. Okay, and then let's see because it's a map, is it? So the constructor, I just use a hash map here. Okay. And then let's see some methods. So we create the hash map. And over here, that's the definition to decide if two vertices are neighbor to each other. Is it neighbor to each other? Of course, these two vertices need to be in this graph. How can you decide? Because this is a map. The map has a, so in Java map, it has a method called contains case to find if it contains that specific key. Is it? So if both vertex are in the graph, then the contain key should return true. If either one return false, that means you don't need to worry about it anymore. So that's why I return false. Okay, return false. Okay, and then let's see. How can you decide if these two are neighbor to each other? So anyway, so that means you need to decide if it belongs to any of the edge E. Is it? And the E dot U is the starting index. And the E dot V is the ending index. Is the ending index. Okay, and then let's see. So can anyone tell me what we have this? Vertex dot get U. What do we get? What is a vertex? This vertices is what? It's a map. And for hash map, anyway, for map, Java map, the get key will get what? What do you get? The return.
Value.
Very good. Yeah, it's values. And what the value is in this case?
List of edges.
Yeah, it's list. Very good. Is it? So what you have, this return is a list. Is it because it's a list, you can call that a stream method. So here I try to use functional programming, okay? Otherwise you need to use a loop, is it? So I do filtering, is it? Because you want to see if those two belong to an edge. So here you have the edge, is a list of edges. Okay, and let's just, so this E is what? It's an edge. Is it? It's an edge. Okay, this is a lambda expression. Why? Because the filter, if you check a Java official document, filter, the parameter is some functional interface. And I don't remember exactly. Maybe it's a predicate or what? Predicate or something. I forgot. Okay, we can double check. So anyway, some functional interface. Is it because it's a functional interface? That's why here you can apply lambda expression. Is it? Anyway, so what this lambda expression is? So anyway, this is an edge. Okay, and you want to see edge is what? V. V is what? It's ending index. Ending index. U is what? It's a starting index. Starting index. Is it? You want to find, because you want to check UV belongs to this edge. As it belongs to this edge. Okay, so how do I? Okay, you will check. If the E dot V is V, because E is from what? E is from U. Is it? E you get from the list of the edge. You filter it. Is it? Okay, and then you find if you do have such one, if you do, that means it is true. As in, so these two vertices are adjacent to each other. Okay, but here be careful because what I design as an edge as directed, so maybe U is ending index and V is starting index. That's also possible, is it? So that's why you need to use V to get the list of all of its edges. Is it of its edges? And then do the same thing. Is it? So this time, a V is a starting edge. Is it? So you can also do. And either one, if it's true, then it's true. Okay. Okay, so that's adjacent. And then let's see the neighbor. And we also very interested in getting a vertex, all of its neighbors. Often the neighbors should be stored in a set. Is it? So that's why over here I use a hash set of the type of what? Vertex to store all of the neighbors. Is it? Okay, the first thing is this may be the starting index. If it's a starting index, and you can get called contains case, is it? And if it does exist in the map, then we get all of the edges that's related with this vertex. Then same thing, we for each of it, is it? Because what this, you will have list of edges, either starting or ending. is it at U? That's what you will get. That's what you will get. So over here, what we consider, oh, I'm sorry. Over here for this case, it's we only consider as a starting index, okay? Starting index, so we can call that for each. Then you can add the ending because you try to find the neighbor that to the set. So over here, you call what set add method. Okay, that's for the starting case, okay? And then over here, we consider U as ending vertex. And for ending, then you need to loop through all of the vertices. So this is graphs get vertex, so it will return all vertices. And then for each of the vertices, is it what you will try to find is U as ending vertex. Okay, so you get a starting vertex from the whole graph. So that's not efficient if your graph is too large. Is it? This is not an efficient way. And maybe you can help me to find some other better way, okay? So regarding my design for this part, it's not a very good design, okay? Consider a huge graph, okay? So, but I just try to explain the idea, concept here. So anyway, so here it's finding of the ending vertex, okay? And when you find either starting or ending, then you find of the neighbors, okay? So that's this concept here. And then let's see the add vertex. Because when you consider a graph, you need to insert a vertex. Is it with a vertex? How do we do it? Because in this case, we use map. Is it? So, and the map has a method called put if absent. And put if absent is, if it is absent, you are going to use to create in, because that's the value part. Is it? You're going to add this key with this new value. Is it? Otherwise, you won't, because if the vertex already exists, then you won't change it. That's what over here, the case. Only if it's absent, then you add this new edge list, okay? But it's not add with the related edge. So each time when you add a vertex, you also don't forget, you also need to consider if it also needed to be added as an edge. Is it? So edge here, we consider the directions from U to V, okay, U to V. So each edge will only allow one direction, okay, U to V. And then let's see over here. So we first need to find, because this is going to be the starting, is it? So you are going to find if this vertex already in the graph. If it is already in the graph, then you are going to add this new edge, UV, the new edge, UV. So what next is we are going to check with, so this is the map. The map's key, then you will get of the value. The value is a list of edge. Is it? That's why you can use this loop. Is it? For each of the edge, then you can see the ending, if the ending matches this. If ending match, then this edge already exists, so you don't need to add second time. Is it? If it is not, then you create the edge. You create the edge, and this is what? This is a list. Is it a list of the edge? And then you can add a new edge to the list. Okay, so that's taken care of the starting vertex already in the graph. And if you want to add a new edge, with the new vertex. Is it all the other existing vertex, but you add a new connection? That's also possible, is it? Otherwise, if the edge doesn't exist, is it? So both vertex, so at least this starting vertex doesn't exist in the graph, then what we can do, you create a new edge. Okay, create a new edge, then you add this, we are going to create a new array list, is it? Because the U is also new, is it? So then you add the list of the edge to this map, and then you add that new edge to the list of the edge. Okay, so that way we can add an edge. Okay, that's regarding add an edge and add a vertex. So then similar, it should also support to remove vertex and remove edge. Okay, so let's see, how do we remove vertex? Remove vertex, and what we get here, the get U. Then here we have the list of edges. Is it list of edges related with U? Is it? And if you just, because you're going to remove this vertex, so if you just call remove the U, is it? Then this is going to be gone from what? From the map. So you remove U from map. Map's key, basically. So map doesn't have this vertex anymore. Is it? So that's this case. Is it? If the list is not empty, as it is not empty. And what else is what that's not taken care of all of the cases, because U may also be the ending vertex. Is it? If it's the ending vertex, you will not get from here. Is it? So if it is ending, how do we find it? Then you need to loop through all of the vertex. For each of the vertex, is it? You check the related list of edge. And if it's ending, then we need to call remove that edge. Okay, because this time you don't want to remove completely, it serves as the key. You just want to remove that specific edge. Okay, but if it's starting, it serves as the map's key, then you want to completely take it off. Okay, so that's remove vertex. And then here we remove edge. So remove edge, then you need to specify both vertex. Okay. And how do we get, so here's the starting vertex. Okay, for the starting vertex, then you can get the list of the edge. Is it the list of the edge? And we said, okay, if it is null, then we are going to loop through. Okay, loop through. And if we can find it, both starting and ending, specify as what you just specify. Is it? And you can find it. If you find it, then you remove it from the list. Is it? From the list. And after you also don't forget, you need to update. Is it? Because this is a map. Is it? Map's value is a list of edge. Is it? And the list updated. That's why your map also needed to be updated. For the put method, the put method is if U doesn't exist, it will add the list. If U exist, if key exists in map, then it will use whatever the updated value, the new value, okay, the new value to update the map. So that's remove the edge, okay. Okay, and for the toString, it's pretty straightforward. So we just try to output the whole graph, okay. So what we do, we loop through the whole vertices, okay, vertices. And oh, for the vertices, if you want to get all of the vertices, you just call the, so this, because it's a map, that you call the key set method, then you get to the set, as you get to the set. And we can do the for each loop. So for each of the vertices, for each of the vertices, then we will output what? The associated what? Associated list of edges. As a list of edges. And then you can output this graph. Okay, so that's this part. And then let's take a look of a main part, okay. So the main part, the first, so I have two graphs. The first graph, G1, I'm trying to simulate some friendship, okay. So the friendship is, so this is kind of like a social media, that you have person and list of friends, so you have the person, the list of friends, okay. So here it describes the relationship. So basically this you can see A and B and B and A, is it? For friendship, it's a two-way, is it? So A and so in our simple graph, is it? So you have AB associated with A, and then when you have B, you also have BA, the edge. The edge, is it? But it's a list of edge, is it? A, B, A, C, and AD, is it? List of edge. Okay, so then in this case, we first create an array of vertices. Then we initiate every single vertex with its ID and label, is it? And label. Then you can just call that add vertex, add each one of it to our graph. But that's not, you cannot just stop here, is it? And you also need to add every single edge, is it? Every single edge, then starting vertex, ending vertex, is it? So over here, then we have the relationship described, is it? So you can just follow that to add all of the vertices. Okay, what is it? In some case over here it says it will not be added to the graph because it's already exists, is it? And after that, basically we can print out our graph. Okay, print out. And then you can check if two friends are neighbor, is it? Are friend. So then how do you check is you call the adjacent, is it? To find if like B and D are friend. You can also find some specific like person B's all of its friends, is it? Of the friends. And over next, you can also remove friendship, is it? Like B and C, so friendship. Then you need to call the remove edge, is it? After that, we can see if the friendship is removed. We can print out the graph, okay? And you can also check if B and D are friend anymore after B is removed, is it? And you will find something. And you can also remove the vertex, okay? Remove the vertex of B, okay? And here, keep checking all of the B's friends so that you can also find if B and C, the relationship is removed, is it? You can also find all of the vertices. At this point, B is not removed from the graph, okay? So it's kind of in your Facebook, is it? you remove one of the friend, but you still have other friendship. Is it? You are not removed by Facebook. Is it? So your account is still exist in Facebook, but this step removes the vertex, then your account is removed by the Facebook. Is it? So your account doesn't exist anymore, or you deactivate your account. Is it? So that's called remove the vertex. Okay, then we can see it. Is it? And after that, if you want to find someone want to find the relationship on the Facebook between you and someone, then they cannot. Is it? And you can still get some other information. Is it? Okay, so that's the first one. Okay, so let's take a quick run to see what we can get from this simple application. So what over here is it? So this is a output of the graph. So within the graph, so for each vertex, so basically here is each person, is it? It shows each person's friend. Is it one-way friend? Okay. So over here, then it also shows B's of the friend. So it gives that. And you can also check if B and D are neighbor. And we can find, okay, B and D. Is it B, D, R, and also D, it's also related with B. They are neighbors. And all of B's neighbors, let's double check. Is it B's neighbor? It has A, it has C, it has D, and it has E. Is it all of the neighbors? Is it? And from the other nodes check, is it? You can also find. And it says after removing relationship between B and C, if you find it doesn't exist, is it? For both B and C, is it? It's cut off, okay. But all of the others are still, both nodes are still in this relationship network, is it? And that's why if you want to see B and D are still neighbor, that returns true. And all B's neighbor, you can see C is removed, is it? And all of the vertices in the graph. So B is still, account still exists. And after you remove B from the friendship graph, from the social network, did you see B doesn't exist anymore? Is it? And all B related is doesn't exist, or cut off. So then if you want to check if B still exists, it will tell you doesn't exist. Is it? And if you want to find if they are neighbor, of course, is it? And when you try to find the C's neighbor doesn't exist, doesn't have B anymore. And all vertices in this graph, B doesn't exist anymore, okay? So, okay, so this is just a very simple graph, okay? So we have some basic idea about graph. And Thursday we can discuss more. So I think that's all for today, okay? Quite a lot of, later I'm going to post all the information to our course website, okay? Okay, bye.
Bye.